Start anytime.
Let's get started. So everybody, welcome to day 2 of the C3.ai DTI workshop on data-driven decision-making in socio-technical systems. Today's focus is on mobility, transportation and mobility systems. My name is Claire Tomlin from UC Berkeley, and I'll be moderating this session. We have 3 wonderful speakers lined up. Okay, so for our first talk this morning, which is called Control of Mixed Autonomy Traffic via Deep Reinforcement Learning, and it will be given by Professor Alex Bayen, who's a professor of electrical engineering and computer sciences and civil and environmental engineering at UC Berkeley. Alex is actually the Liao-Cho Professor of Engineering at the University of California, Berkeley, and he directs the Institute of Transportation Studies. He is also running the aerospace, the design of aerospace programs at UC Berkeley, where we're recently starting to plan a new undergraduate major in aeroastro in the College of Engineering. So Alex works in transportation systems. He's a specialist in transportation systems. He's authored 2 books and over 200 articles in peer-reviewed journals and conferences. And he's won a number of awards for his research, which, his research projects include Mobile Century and Mobile Millennium, for which he received the 2008 Best of ITS Award for Best Innovative Practice at the ITS World Conference, and an award from the California Transportation Foundation. He's also the recipient of the PECASE Award from the White House in 2010, the Okawa Research Grant Award, the Ruberti Prize from the IEEE, and the Ruberti Prize from the ASCE. So thank you, Alex.
Okay, so first, I'm drinking out of my MIT mug today. I wish I was in Boston. Thank you to all the organizers, Saurabh, Asu, Alex, Claire, Shankar, Larry, everybody. I'm really excited to be presenting today. I'm going to talk about control of mixed autonomy traffic via deep RL, and I think the talk is about 15 minutes, starting now. First, I want to acknowledge Kathy Wu, who is a professor at MIT, because I think even though this project has grown considerably since she was a PhD student, I think she was really the one who had the vision of using deep reinforcement learning for microsimulation in the context of Lagrangian control of traffic. And so I think that vision really needs to be acknowledged. So Kathy, if you're listening, thank you again for all your work. And as I mentioned, this team has grown considerably now with about 50 people working on the project out of 5 different campuses, a few auto manufacturer companies, Toyota and GM in particular, and about 50 students across the whole team. So what I'm presenting is very high level. Do not expect that I'll go in depth. I think maybe that will come through the panels, but hopefully I can give you a sense of the vision and where the project is going. In one slide, the idea is relatively simple. For those of you who know time-space diagrams, these little green diagrams, the horizontal axis represents time, the vertical axis represents location on the freeway, and the color represents speed. And what you see are stripes corresponding to stop and go waves. I think all of you probably have been at some point in traffic where it starts, it stops, it starts, it stops, and nobody knows why. These so-called phantom jams or stop and go waves are one of the materializations of instability of traffic, essentially the inability of the human to properly regulate some mechanisms. And what we do is, our goal is to pioneer the field of Lagrangian control of these systems, which is how do you use, if you see my mouse hovering, these kind of automated vehicles at very low penetrations to regulate traffic. So you can think about this as regulations of humans by robots, except everybody's in the car. And you can think about this as heterogeneous multi-agent control, because everybody has a different dynamics. And then you can put on top of it all kinds of control architectures, centralized, decentralized, etc. Our approach essentially is learning through simulation and understanding how deep reinforcement learning can be used to achieve these goals, which in our case are smoothing traffic. So that means what you see on the right is a much smoother traffic condition. Our goals are essentially to demonstrate with a concrete experiment that if 5% of all vehicles participated to this, so think about Tesla owners or people with very high-end cars, one could decrease the waste in energy of freeways by 10%. which is enormous. Every freeway has a lane that can carry up to 2,000 vehicles per hour. So a 5-freeway lane is 10,000 vehicles per hour. The amount of energy saved would be phenomenal. And we hope to demonstrate that not just with simulations, but in reality next year in Nashville, Tennessee, with a major experiment. So I'm going to talk to you about a few thrusts in the program to explain how we work. So the first step is traffic modeling. And I think this is where Kathy Wu was really visionary in that. Micro simulations, which is the simulation of every possible vehicle on the road, is something that has only become a reality 10 years ago because of the rise of computational power. But learning over micro simulation is something that has only become a reality now because of other advances that I will talk about. And so I think the first step in doing that work is to have the ability to model major corridors like the one I'm showing here in order to be able to learn over these simulations. So it's really learning over simulations and then doing transfer learning. The second step is to do energy modeling. And if you want to have a serious contribution to the field, I think it's important to work directly with auto manufacturers. So one thing we do is we produce these models, reduced order models of vehicle classes, trucks, pickups, buses, regular cars, blah, blah, blah. And through some collaboration with the Oregon National Labs, which has built a fantastic library of hundreds of these models through the autonomy framework, we're able to essentially come up with reduced order models of these vehicles to have a very precise model of their energy consumption that are then helped to define the reward functions that we design for the reinforcement learning algorithms that we develop. I think that's very important because that's what makes our work different from toy example and toy problems. At the end of the day, we will be able to characterize the class of every vehicle on the freeways. I'll show at the end of the talk how. So having these precise models is important to do real computations. Now, there is a significant amount of the work that is also theoretical in nature. So, for example, one of our approaches pursued by this group consists in using partial differential equations, in particular mean field games and mean field approximations, to model the flow of traffic, which is essentially the three coupled PDEs you see on the top. So that essentially models the flow of traffic as a mean field, and then modeling the automated vehicles as a set of ODEs that plug onto that field. So you can view this as a one-way coupling where the ODEs influence the mean field and are used to control it. I'm not going to go in depth of all the theorems we can prove on this, but this is to show that there is a very theoretical approach to this work. It has a lot of interesting theoretical features. It also has its limitations when implemented in reality, but it is something that we are very actively pursuing, and that's mostly done by the Rutgers campus in collaboration with Berkeley. Now, obviously, in terms of implementation, the reinforcement learning part is the part that is most likely going to be at least deployed first. And again, I want to mention Kathy, because that's really started during her PhD at Berkeley, and that's now work that she's carrying at MIT. But the whole vision started with a project called Flow, which was the first integration of microsimulation with the reinforcement learning libraries on the AWS cloud that has then grown a lot in this project. And I think the important thing in the work we do is that there's essentially three categories of agents in that system. There are the controller agents, which are the red cars. So think about it as your level 2 vehicle that can be activated to smooth traffic, maybe by going faster, going slower, or switching lanes. Then there's a second category of vehicles, which are the vehicle it can see or sense, usually the vehicles in front. So they're depicted in blue. And then most of the vehicles, it just doesn't even know they're there. They're just part of the dynamics, and these are the white vehicles. And so a lot of the work we do has to do with understanding the proper constructions that we have to operate to be able to actuate these systems. But in reality, in general, at least in the near foreseeable future, the connected vehicles do not communicate with each other, and they don't receive a lot of information about the rest of the traffic. So even though in the future you could think of an architecture where they receive more information and ultimately they communicate with each other, that's not happening over the next 5 years or 10 years. And so part of the issues in building these algorithms is being able to build algorithms that do not require these proper architectural considerations because they're not there yet. And so the way it looks in practice is the following. This is an example of the I-210 in LA. What you see in the movie streaming now is red cars, and you can see the waves coming in. At that point, now blue cars have turned on. That means the smoothing is happening. And when you look at the simulation, and if you keep watching, what you'll see is that the waves are progressively eliminated. These have been done in simulation. We're now transferring them over to hardware platforms. I think what's remarkable here is that we're learning over microsimulation, something that could not be done even 5 years ago. And the policies that we're getting from it are actually implementable in real hardware. And so, for example, the penetration studies we do are demonstrating already that with 10% of these vehicles, it's amazing how smooth you can run these flows. And what's even more amazing is that if you look at the policies, there are a lot of human hand-tuned controllers that maybe have provable guarantees of safety or performance. But the deep neural nets that we're training are not only able to almost match their performance, so that think about the blue curve as the performance curve of our algorithms on the different parameters such as speed limit and fuel efficiency. Think about all the other curves as things that have been handcrafted using control theory, have some guarantees, but what's remarkable is that the deep reinforcement learning not only matches their performance in most cases or surpasses them, but also does not require information such as downstream speed to function. And that's kind of remarkable. And in the discussions, we can try to discuss why that is and how that relates to interpretable AI. But in the interest of time, I also want to show the rest of the project, since I only have another few minutes. So we also built a full data pipeline and dashboard. So again, this is building on Kathy's work, but now we've expanded it so that we have a leaderboard. And you could think of that leaderboard as a Mujoko of traffic, if in a sense, where people can check in their algorithms. And then based on how well they do, they're ranked. And then based on their performance, some of these algorithms will be migrated to actual hardware platforms. Speaking of which, the Arizona team, led by John Sprinkle, is now instrumenting a lot of cars. So some are at Berkeley, some are at Arizona, some are at Vanderbilt. And this is an example of the data they see and the Carla and Gazebo implementations of their surroundings so that we can test the controllers in a virtual environment once they're developed. And ultimately remote control the vehicle. So this short video clip shows you how you can remote control a vehicle just with a joystick. The idea is that the commands input by the joystick will soon be the AI policies that we developed through the previous section I just showed. So here's John remote controlling his own car through a joystick, and probably in a few months when I give my next talk, maybe in this venue or another, we'll have instead the AI policy driving the car. Finally, we're going to do major testing in Tennessee. And so this project has been also leveraging a multi-million-dollar, I think $10 million by now, investment from the Tennessee Department of Transportation to instrument an entire freeway with high-resolution cameras so we can ultimately move to pixel learning and use a lot of the machine vision algorithms that are used for system identification. And so to give you a sense of the magnitude of that part of the project, this is the Tennessee Department of Transportation installing these gigantic poles that we will use to measure the efficiency of our experiments next year. These are erected now every 500 meters. And I think the plan is that the I-24, you can see it being erected as we speak now. The I-24 will probably have a couple dozens of these. So we have full visibility of the entire experiment as we run the experiment. And of course, these will be used for a lot of other purposes, such as traffic management. But you can see that with that, we're going to create a gigantic data set like never before that will have the highest resolution video data of traffic and actuation of traffic, kind of like the NGSIM was 10 or 15 years ago, but obviously this is now much more advanced. And to finish the presentation, this is the preliminary data as it looks today. So you can see the granularity is quite spectacular. And part of what we're excited about is that with standard deep learning strategies, it's very easy to extract the vehicle class, which will enable us to map it to our very accurate modeling. So with this, I'm going to stop to stay in time. I just want to acknowledge this is a huge team over 5 campuses with a lot of sponsors, in particular the US Department of Energy, but also NSF and many others. So I want to really thank all of the people who have participated to this, and I'll be very happy to go more in depth on any of the 5 thrusts I mentioned, maybe in the discussion section. And with this, I think back to you, Claire.
Thank you very much, Alec.